let's continue with quantum circuits. So what we use to describe quantum circuits is what we call a circuit model, which is a sequence of some building blocks which carry out our computations. And those we call gates. So the way it looks like is we have some wire coming in from the left. So we always go from the left to the right. From the left, we have some wire coming in, that's the input. Then we have our algorithm or our gate. Our algorithm can consist of multiple gates. And then we have some output wire or multiple output wires. So let us start with considering single qubit gates. So as the name suggests, that means that we look at gates that act on a single qubit. So before looking at actual single qubit gates, let us look at how a gate on a classical bit would look like. So a classical example of a gate on one bit would be the NOT gate. So I have as input state either 0 or 1. Then I have my wire. I have a symbol which reflects the NOT gate, and then the output is 1 or 0. So the NOT gate just flips the bit. So if I input 0, I will get 1. If I input 1, I will get 0. Now for a quantum example, we will look at actually a lot of different quantum examples. We will look at different gates, different standard gates. So, but first of all, we know that quantum theory, or one of the postulates of quantum theory, is that it is unitary, which means that quantum gates are always represented by unitary matrices. And a unitary matrix, for those of you who are maybe not too familiar with linear algebra, a matrix is unitary if U dagger, and now dagger is this T again, which refers again to the transposed and complex conjugated version of the matrix. If U dagger times U equals the identity matrix, which I write with this. This is 1. Identity matrix is the matrix where we have just ones on the diagonal and zeros everywhere else. If this holds for a matrix, then we call this matrix unitary. So we will not go into that too much because all the matrices that I will show you now are all gates that are all unitary. Of course, we will not prove that, but just you know what the definition is. And maybe let's quickly recall from our Dirac notation, the Dirac notation, because I think it will help you now if we write, because you want to write the gates in Dirac notation as well. If I have a unitary that I can write as U00, U01, U10, U11, 2 times 2 unitary, then the way I would write this in Dirac notation, remember with the brass and with the cats, would be the first element. I can write it as 0 times 0, U0 times 0, 0. This gives us this element. Because if I have this 0 cat, 0 bra, that would give us a matrix that looks like this. Then I have plus U01 times 01, because this would give us a matrix, give us this matrix. Okay, plus U10 times 10, plus U11 times 1, 1. So this is if I want to write, now this looks maybe complicated, but you will see for the other gates, it simplifies sometimes to use the Dirac notation instead of the matrix way to write it down. So this is a general way of writing down a matrix. And let's consider some gates. As a first gate, we will look at what we've seen before, the sigma X gate, the Pauli X gate. The Pauli X gate is given by 0, 1, 1, 0, And now writing this in direct notation, we can write it like this. Because the prefactors are just 1, the other elements are 0. So this would be our direct way of writing this Pauli gate. Now to see what effect this gate has, we will apply to the state 0. Question is what happens if we apply the x gate, sigma x gate, to state 0. And we can determine this by just either we can choose matrix multiplication or we can choose the direct notation. I will show you both. So if we use the matrix multiplication, we just take the matrix and multiply it with our vector. Importantly, we always take the matrix from the left. So if we have multiple elements, the first matrix is the one on the very right. And then the more you go to the left, this all happens later. Follows. So now if we do my matrix multiplication, I hope you're familiar with that. I take the first element here from the matrix, the 0, and I multiply it with 1. And I take, which gives 0. So I have 0 times 1. So I'm taking this one. Then I'm taking plus 1 times the 0. So I'm getting just 0. And then for the second row, I will not do it this slow every time, but just for people that aren't familiar, maybe, I'm taking 1 times 1. Oops, sorry. Sorry. So I'm sorry, I'm taking 1 times 1, plus then this 0 times the 0. So I'm getting 0, 1. Okay. So I will get the vector 0, 1, which is our state 1. Now let's check what happens if we apply the sigma x gate to our state 1. And now this time, let's do it with the direct notation. So we have our matrix, which we now write with cats and bras, times the state 1. Now we can just write it as 2 different terms. It's linear, so we just write 0, 1, 1. We multiply the 1 in both terms, plus 1, 0, 1. And now what we can notice is here we have the inner product of 1 and 1, which is 1. Here we have the inner product of 0 and 1, which is orthogonal, therefore 0. So the second part is 0, and we only have state 0 left. So what this gate then corresponds to is to a bit flip. So it is just like in the classical computation I just showed you before, the NOT gate. And this is the quantum equivalent of the NOT gate, because what it does is it flips the gate. If we input 0, it gives us back 1. If we input 1, it gives us back 0. So for example, if I have 0 as my state here on the left, then I have the wire, I have my matrix sigma x, and then the final state will be 1. What this gate in general, I could also not only input, so this is the quantum equivalent, which means, first of all, it can act on quantum states. But so that implies that it can not only act on 0 and 1, but it can also act on superpositions. And so what it does in general is it is a rotation around the x-axis by pi. So if we go back to the Bloch sphere that we had here, and so if we go from, we have the x-axis, and you can now think of it as a rotation, as I said, by pi, so just halfway by 180 degrees. So if we around the x-axis, the axis that looks towards us. So if we are in 0, we go down this way to 1. If we are, for example, in plus I, one could also just by this geometrical description, this graphic description, if we now rotate around the x-axis, we would go halfway around, and we would go from plus I to minus I, and from minus I to plus I. If, however, we start with the plus state, for example, since it is on the x-axis, if we rotate around the x-axis, it will stay there. So on the x-axis, on the plus state, this gate will not have any effect. If I apply sigma x to the plus state, I will get the plus state back, and same for the minus state. So those states lie on the axis. But okay, let's continue with the next gate. The next gate is the sigma Z gate, the Pauli C. We have seen that one before as well. And in general, so the description is 1, 0, 0, minus 1. And if we want to write it in Dirac notation, we can write it as 0, 0, minus 1, 1. I can tell you now already this effect will not have any effect on 0 and 1 state, on the state 0 and 1, so we will not consider that now. But let's instead look at what happens when we apply it to the plus state. If we apply to the plus state, let's do it again in matrix notation. We have our matrix. We multiply it with the plus state. The plus state is 1 over square root of 2 times 1, 1. And so we can get this prefactor to the front. And then we have, if we do matrix multiplication, we get 1 and minus 1. And this is exactly the minus state. And in a very similar way, if we apply sigma Z to the minus state, let's do it again one more time in Dirac notation. If we do this, and we multiply it with the state 0, minus 1, then we can see most of the factor, 2 of the factors actually cancel, because if we multiply this, if we have the bracket of 0 and 1, it's always 0. So the only terms that we keep when we have 0 and 0, and then we have the 0 left, and when we have 1, 1 on 1, so we have then a minus times minus, so we get a plus. So we get 0 plus 1, which is the plus state. Since we go from, now in this case, from plus to minus, so from 0 plus 1, we go to 0 minus 1. We call it this time not the bit flip, but the phase flip, because it flips, in this case, the phase of our, the relative phase between 0 and 1 for the states plus and minus. In general, what it corresponds to is a rotation around the z-axis. And again, by pi, by 180 degrees. That's also, by the way, why it does not have any effect on the state 0 or on the state 1, if we act on that. Because since we rotate around the z-axis, if we're already on the z-axis, just as before, it will not have an effect on those states. Okay, and now I guess you can already guess what the next gate is. The next gate is the sigma y gate, Pauli y. And it is given by this form. And now one thing that one can note is that this actually also corresponds to I times sigma x times sigma z. Which means that we're not going to do any calculations now, but I will just tell you, because you can write it as a product of sigma x and sigma z, it's the same as if we apply a bit and a phase flip. And of course, in general, it's a rotation around y. So, because, well, on the Bloch sphere, actually, if we do first a rotation around x and then a rotation around z, both by pi, then in the end, that would be a rotation around y, also by pi, by 180 degrees. Now, these matrices are, well, quite important in linear algebra because they have a lot of nice features. And we call them, as I now said several times already, we call them the Pauli matrices. And for each of them, if we square them, we get identity. You can calculate that by just multiplying 2 times the same matrix. You will see we will always get this identity matrix. Identity matrix means basically that we're not doing anything at all. If we apply the identity matrix to any state, we will get the same state back. So that also tells us that if we apply twice the same gate, we will basically do nothing. So if I apply 2 times the sigma x gate, I have 2 bit flips, and then I will be back at the flip at the state I had before, which you can also see on the block sphere because I told you it's a rotation by 180 degrees. If I now apply it twice, I have a rotation by 360 degrees. So I can just, it has no effect. So we have the Pauli matrices and the identity. And the together, so the Pauli matrices together with identity. Together they form a basis of 2 times 2 matrices. Which means that any one qubit rotation can be written as a linear combination of these gates, which is something that is, for example, very important once we look at error correction, which you will learn about on Friday. So these 3 or then 4 gates together form a basis and have therefore some nice features. Now there's one last gate, or maybe 2 more gates that I really want to tell you about. So in my opinion, the most important gate that you will learn today, the most important single qubit gate, it's called the Hadamard gate, and you will find it in any quantum circuit that you're gonna learn about. You will find this gate. You will see in a minute why. So the description of the mathematical description of the Hadamard gate, we write it as a matrix. We write it this way. Again, by the way, you see the prefactor of 1 over square root of 2. We need that prefactor to make sure that we have a unitary matrix. And if we want to write it in Dirac notation, it would be this. Now, if we apply the Hadamard gate to state 0, then what we will get, we have this prefactor 1 over square root of 2, and here we get 1 and 1, which is the plus state. And if we apply the Hadamard gate to state 1, I will not do the calculation now, you can believe me or do it yourself, we will get the minus state. Which means that in general, this Hadamard gate, what it does, or what it's used for, is to create superposition. Because if we have a quantum circuit, if we run a quantum circuit, in the beginning, if we initialize our qubit, we usually initialize it in the 0 state. So the quantum circuit usually starts with all qubits. Every quantum circuit starts with all qubits in the 0 state. If we then apply a Hadamard gate to each of these qubits, they will all be in a superposition. So we will immediately get this, superposition of all possible states, and then calculate and do our cool stuff on all those qubits at the same time. So this is the reason why basically any circuit you're going to learn about will in the beginning start with Hadamard gates, as you will see. Something else that holds is that if we apply the Hadamard gate to the state plus, we'll get the 0 state. And if we apply to the state minus, we will get 1. So we're actually going back and forth. We can if we apply to state 0, we get plus. If we apply to state plus, we go back to 0. And the same with the 1 state and the minus state. So we can use this to change between the different bases. So experimentally, for example, we usually cannot do an X measurement. We could, but what we do is we measure in the Z basis. We measure whether it's 0 and 1, the 0 or the 1 state. And if I give you the qubit, if we would like to do an X measurement, what we do is we first apply a Hadamard gate and then do a Z measurement. Applying first the Hadamard gate and then doing the Z measurement is the same as doing an X measurement, at least mathematically. Of course, you can always have some noise and some errors, but for now we're going to talk about the mathematics behind it. And then, so applying Hadamard gates and the Z measurement equals applying an X measurement. And in a similar way, we have the gate S. So this is now the last single qubit gate I will show you. So it's similar to the Z gate, but instead of a -1, we have the I here. So it's basically if we apply S twice, we will get the Z gate or Z gate, maybe to have less confusion. And so what this gate does, it instead of the, we know the Pauli Z gate rotates us around the Z axis by 180 degrees. And this is basically half of it. So what the S gate does is it adds 90 degrees to the phase of phi, the phase phi. So if we apply S to the state plus, we will get the state plus I. If we apply S to the state minus, we will get the state minus I. So if I show you again on the block sphere, can you see the block sphere? Yes. So on the block sphere, if I start in the blue state, the plus state, blue plus state, and I do this S gate, I will go to from the X axis to the Y axis. If I apply it again, I will go to the minus state. Then I will go to the minus I, and so on. So I can turn around. And so what it's used for then is if I apply S times H times the Hadamard gate, then instead of changing between the state 0, between the X and Z bases, we change between the Z and the Y bases. So if I want to do a Y measurement, I would do the same. I would apply S and H and then do my Z measurement, because that's the physical one. Okay, so now there's some time for questions. Brian, do you want to read the first question?
I would love to. So we have a good amount of questions on here, and just a reminder to everyone in the chat, please upvote questions when you have one in here. I see a lot of people still typing them in the chat, but we're using the upvoted questions and answers list to find the top one. So please make sure you're upvoting those. Right now, our most upvoted question that doesn't have a full answer here is Broad describes a quantum state, superposition of 0 and 1. How do I imagine a ket?
Well, first of all, the quantum state, usually if I actually the way I'm writing quantum states now is I'm just writing the ket, not the bra. So I'm writing this kind of thing, which is a ket, not a bra. So if I'm writing a superposition, I will write it as 0 plus 1, for example. So that would be, I'm using kets to describe quantum states. The reason it's a bit hard to explain, because we do not talk about mixed states now, but only about pure states. For pure states, a quantum state, if I want to look at a density matrix, which is the actual way to describe any kind of quantum state, both pure and mixed, I would always look at a state. If it's pure, it would always have this form. So both the bra and the ket would always be the same for pure states. So the actual quantum state would be the bra times the ket. It would actually be described by a matrix. But since we just look at pure states, and it's easier then to describe it by just using the ket. But in theory, you can think of both of it. It's both vectors that both help to describe the quantum state. Given the pure states, you can, either of them would just be describe our quantum state.
Okay, thank you. Next one, looks like a question about Pauli spin matrices has been sufficiently answered, so we're going to move that one out. Again, if people have answered these questions in the comments already, we're going to consider that answered. Next question that's highest is, what is exactly eigenstate, or what exactly is eigenstate?
I actually see that someone answered it already, but okay. So the eigenstate of a matrix is a vector for which holds, let's say I'm given a matrix A, and then the eigenstate of a vector of this matrix is any vector for which holds that, so this is a matrix, and for the eigenstate holds that A times X equals, let's say, lambda times X, where here we have again the same eigenstate, and where lambda is just some number. This is, well, I will not go into much detail now. So that's a mathematical thing that you learn about in linear algebra, and these eigenstates have a lot of important features. But so this is the mathematical definition of an eigenstate. Yeah.
Great. And then last question for now. This user said, I'm curious about the Qiskit logo. It is a block sphere, but there's a specific state or phase on it. Is there one that's being displayed?
That's a very good question. I'm actually going to answer that in an hour when we will look at the Q sphere, because it is not a block sphere. On the block sphere, I will, yeah. You will get the answer in an hour when we introduce the Q sphere, which is like the block sphere, but on multiple qubits. So the Qiskit logo is actually a state that describes a state on multiple qubits, not just on one single qubit.
Perfect. Thank you very much.
Okay, then let's continue with multipartite quantum states. So, by the way, I just noticed that I cannot see that on the screen now. Can you see any text on the screen? Oh, okay. Here we go. Okay.
My fault. Sorry about that.
Good. So, but I guess then now I should not write on the very bottom, right? Can you see that? What I'm writing right now? No. Okay, good to know.
So I've been zooming in and out and trying to scroll as needed. People in the chat are asking to be able to see the text at a larger size, but that just means we're zooming in and out at different ways.
Okay. I mean, I can also write larger if that helps, or
probably both. Let's do both and start from there.
Okay. I'll try to write a bit larger then. So we use multipartite quantum states, as the name suggests, to describe multiple quantum states, to describe quantum states on multiple qubits. So what we use to do that is tensor products, which is another thing that some of you might have heard from in linear algebra. So the way it works is I have two states. I have state A on one qubit and state B on the other qubit. So just two vectors, A1, A2, tensor B1, B2. And now if I take the tensor product of two two-dimensional vectors, I will get one four-dimensional vector. What I'm doing is I'm taking the first element of the first vector multiplied with the first element of the second vector. Then the first of the first vector times the second element of the second vector, and the same with the other two elements. So I'm getting a four-dimensional vector. To give you an example, let's say system A is in state 1. I know I put this small a here to determine which Hilbert space, or which particle I'm talking about, or which qubit I'm talking about. So if I'm doing this, now I'm talking about qubit A is in state 1. And then I have the system B, or qubit B, which is in state 0. And I have a small b here, so you know which one I'm referring to. Now the total state, and I call this a bipartite state because it's on 2 qubits, is given by, so a short way to write it is this, 1, 0. People just, it's not 10. It's just, people write it this way when what they actually mean is, I will also use that way, by the way. So it's, yeah, just shorter. It means I'm in state 1 on A, tensor 0 on B. Now I can write the vectors for both of them. And if I do the multiplication that I just described, the tensor multiplication, I get 0, 0, 1, 0. So this is how I would describe that state on 2 qubits. If I have even more qubits, then I can do that again. And for example, on 3 qubits, I would get 2 to the power 3. So I would get an 8-dimensional vector. And then it scales pretty fast. This is, by the way, then what we call the state vector. And the state vectors, if I have a state vector, for example, on 10 qubits, it would be 2 to the power 10, which is 1024. So I would have a vector with 1024 elements, which is the reason why simulating quantum computing is sometimes, well, the few qubits you will get, at some point you get to the limits, right? You cannot do it easily for 100 qubits. So yeah, because it scales so fast. So this is the state vector of the state 1, 0 on 2 qubits. And our remark for the state is if a state is of this form, and with this form, I mean something like some state on A, tensor some state of B. Then it's called uncorrelated. But so they are also other bipartite states. That cannot be written in this form. So they cannot be written as some state psi on A, tensor some state phi on B. If they cannot be written like this, then we call these states correlated. And sometimes they're not only correlated, but even what we call entangled. So all states that are entangled are also correlated, but not every state that is correlated is entangled. So you can think of it like a very strong correlation that only happens in quantum mechanics, that we cannot have classically. And we will talk about that actually in the third hour a lot, or at the end of this hour. So one example is the psi 00 state, which we'll also look at later, just to write it down already now so you see what I mean. I could have a state that is in a superposition of 0, 0 and 1, 1, which is something I cannot write it as 0 plus 1 times 0 plus 1, because then I would get 4 terms in total, right? If I would write down state A as 0 plus 1, state B as 0 plus 1, I would get 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. I would get 4 terms. If I only have these 2 terms, I cannot write it as a product of just 2 states. And if I give you this, can give you the state vector of this form, it's actually, well, so 1 over square root of 2 is the prefactor, and then we have 1, 0, 0, 1. Okay, so the first one corresponds to the state 0, 0, and the last one corresponds to the state 1, 1, if you look at the bipartite description. The state that I just wrote down is, by the way, a so-called Bell state, which I will talk about later. And it is used, for example, for teleportation, the protocol that we're going to look at next hour, but also for cryptography and Bell tests, and has a lot of applications. But yeah, you will learn about that very soon. For now, maybe, actually right now, is there already maybe one question on multipartite quantum states? Or, oh, actually, Brian, I see there's a question that is not on the topic, but that you might want to answer.
I saw that question about the increased playback speed. When you play it back, I believe there is an option. I'm struggling to remember, so I will research that for you.
And then someone, okay. So there seems to be not a question yet on multipartite states, but maybe I'm just answering this one question that is highly most voted now.
Sure. Yeah, and I'm sorry, I was scrolling through looking for the same thing, but I do see there is a question in the chat.
Oh,
Why? Oh.
I just broke down. Oh my God, I'm sorry.
No problem. I saw two questions in the chat. I'm not sure if either one of these are aiming at what you were saying, but one is, why can bipartite states not be written like that? And then another is, can you give an example of a correlated state that isn't entangled?
A correlated state that is not entangled? That is a very good question. However, so correlated states that are not entangled are only mixed states. So actually, if we have pure states, I was about to tell you that when I introduce entanglement, if we have a pure state that is correlated, it is also entangled. So this, for classical states, if they are correlated, that means they're always mixed states. I will give you an example for that later. But yes, I will not write down the description now, because then we need to change the formalism from not writing cats but writing density matrices, which is going too deep into the topic now. And sorry, did you say there was another question?
Yeah,
was there two questions?
Was, I'm sorry, I'm pulling it back up. No, apparently I just lost it. So why don't we move on, and then I'll try to find it for you.
Yes, sure. No worries. Yeah, good. So now that we know how to describe states on multiple qubits, we can continue with 2-qubit gates. And as before, we will start with a classical example. So a classical example of a gate that acts then on 2 bits is the XOR gate. So for the XOR gate, I take 2 inputs, call them X and Y. And then I have my XOR gate. And what it outputs is X plus Y, where this plus means that I'm taking the 2 bits and I add them and I take them modulo 2. So if I input 1 and 1, I would get 2, but modulo 2, I'm getting 0. So if I input 0, if what it basically does is, if I have 2 bits that are the same, it will output 0. If my 2 input bits are different, then I will output 1. However, now a problem with this gate is that this gate is irreversible. Because if I give you the output and I tell you the output is 1, then what you know is that either X or 0 are 1, but you don't know which one of them. So you cannot construct the input from the output, which means that it's irreversible. But what we just learned before is that quantum theory is unitary. Which means that we only consider unitary gates. And unitary gates are always reversible. Because I told you before that the condition for unitarity is U dagger U equals identity. This is actually also equivalent to, at least if we look at square matrices, which we do, that U to the -1 equals U dagger. And so the inverse of a matrix, so which is U to the power -1. So we do not mean 1 over U, but we mean the inverse with that. The inverse always exists for unitary gates. So what this tells us is that we cannot just create the XOR gate with quantum computers, which sounds like a big disadvantage. However, let's look at quantum gates. I will give you an example of a quantum 2-qubit gate. We look at what we call the CNOT gate. The matrix for the CNOT gate is given by this. And then if I want to write it in Dirac notation, just to get more familiar with that. So this is basically, we have 0, 0, 0, 1, 1, 0, 1, 1. If you think of the Dirac of the basic states. So the first one corresponds to 0, 0, 0, 0. And we have 0, 1, 0, 1, 1, 0, 1, 1, and 1, 1, 1, 0, which are the 2 ones at the bottom. So if we apply the CNOT gate to the state 0, 0, on X and Y. We have our CNOT matrix times the state vector that we get for the state 0, 0, which is just 1, 0, 0, 0, as we learned before. And now if we apply this matrix, we can easily see that we actually get the same state back. So we just get, again, state 0, 0. If, however, we apply the CNOT gate to the state 1, 0, what we will get back is the state 1, 1 on X and Y. So let's make an input and output table. If we have, we have 4 possible basis states as input: 0, 0, 0, 1, 1, 0, 1, 1. This is X, and this is Y. Now the output for 0, 0, as we just saw, is 0, 0. The output for 0, 1, I can tell you it's 0, 1. Doesn't change. For 1, 0, however, we will get 1, 1. So I just wrote down. And for 1, 1, we will get 1, 0. So if we look at the output, what we notice is that the first output bit that we get back always equals X. While the second output bit that we get for 0, 0, we get 0. For 1, 1, we get 0. In the other 2 cases, we get 1. So it's exactly the XOR of X and Y. It's X plus Y modulo 2. So if we write it as a circuit, we can write our state X and the state Y. And then the way someone writes it, we usually write it is this way. And the output will be X and X plus Y. So what it does is it computes the XOR gate, but it is also reversible because we also get the X back. If I give you the X and the X plus Y, then you can always recover what the input was given the output state. So this is basically the CNOT gate, is basically a reversible version of an XOR gate. So we can just calculate XOR and get X back. Now the reason, maybe just to mention why we write it this way, or also why it's called CNOT. It's called CNOT, is a short form for controlled NOT. Controlled NOT, it's called controlled NOT because controlled on the state X, and controlled is this dot here that I'm doing. This thing is what we mean. Whenever we have controlled gates, we make this kind of thing there. So we control on X, and then controlling means if I'm in the state 0 on X, I will not do anything. Nothing happens. And you see our output is just the same as before. We can tell for those 2 cases here, input and output are the same. If, however, X is in 1, and we're controlling on X, then I'm flipping the state on Y. It's more beautiful. That's how it's supposed to look. Then I'm adding this bit to Y. So I'm adding it on, but then modulo 2. That's why I'm getting the XOR output. And that's why it is like a small plus. The effect on Y looks like a plus. Controlling on X, I'm doing an addition on Y. This is what the controlled NOT and NOT, because we called the NOT gate is the one that flips the bit. So then it flips a bit if X is in 1, if X is in 0, it does nothing. But yeah, so what one can show is that every function f can be described by a reversible circuit. So whenever I ask you to compute something, I can, if it's a classical computation that is irreversible, I can always compute the same thing and somehow make it such that it's a reversible circuit, that you get additional outputs so that we can in the end recover the input. Which means that quantum circuits can perform all functions that we can possibly calculate classically. So there's no disadvantage. Even though it has to be reversible, it's actually even better then. We can always create gates in a way that they are reversible, but still perform any computation. And then also, of course, the CNOT gate. Now in the input-output table, I only looked at the basis states. But since everything is linear, we can also just, like, it works the same way with superpositions. And I can input any superposition state or any entangled state and just apply the matrix as it is there, the CNOT gate. Just apply it by multiplying the matrix with whatever state vector I have.